Sorry, I hope you don't find the picture inappropriate. I found that gas laws, and we're going to look at some applications today of some stuff we did in class. Boyles Law. What is Boyles Law saying? Well, it's a gas law, so it's talking about gases, and the red particles in there would be gases flying around some sort of container, like a metal container, propane container or something. So, if we put a thermometer in here, don't forget these gas particles would be flying around. Okay, so they'd be moving around, bouncing against the walls, and that's what creates pressure in the first place, of course. So, if we set the temperature, let's say it's 25 degrees Celsius in the container, that means the particles on average are moving about the speed of 25 degrees Celsius. And it would create a pressure on the walls. What Boyles Law says is, if we make this container, we'll make it smaller. So let's make the container smaller. And we're going to keep the amount of gas the same. So we'll put the same amount of gas in there of 16 particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You can see, first of all, that they're crammed in there now, but there are a couple assumptions. One assumption is that we're going to keep the temperature the same. That means the particles are all moving the same speed. But if we, so they're all moving the same speed, so 25 degrees Celsius in both containers, but if we make the container smaller, what happens to the pressure? Well, take a sample. Let's take a little sample from this one, say that much space. Take the same size sample in the other container, and you can see this one has about 4 particles, this one has almost 9 in it. You can see there'd be more particles packed in the same space, so they'd be hitting the walls more frequently in this container. So what happens is, if you keep the temperature the same, temperature is equal to the same, you keep the number of particles the same. If you make the container smaller, the pressure will go up. So basically, you have a large volume here, a small volume here. You have a large pressure here, you have a lower pressure here. So another way of stating Boyles Law is simply this. As long as these two stay the same, if you increase the volume, you will decrease the pressure. So that's Boyles Law. Now you could write it the other way around. If you decrease the volume, which is more like what I did in my picture, you will increase the pressure. How about good old Charles' Law? Well, a little harder to understand, but basically I got a container here like the last one, and it's 25 degrees. So the particles are bouncing around in there for a gas, and they're bouncing off the walls, and they're creating pressure. Well, if I make the container, or if I increase the temperature, so if I start heating this up, for example, so I start heating this up, the particles will start moving faster. So if I start heating it up, they would start moving faster, and the temperature would increase, and what would happen is you would eventually start increasing the pressure in the container. Well, what if I don't want the pressure to increase, but I know the speed of the particles is going to increase? In other words, you know the temperature is going to increase. So how do I go from, for example, 25 up to a 50 degrees and not get the pressures to change? Well, the answer to that is make the container bigger, and then those particles, even though they're moving faster than they were, those are particles with arrows on it, they have more space. And so they're moving faster with more space, so I can get the pressure equal in my two containers as long as I increase the volume. In other words, if the number of particles stays the same, if temperature increases, you would also have to increase volume if you want pressure to stay the same in the two containers. I think I'll rewrite that right here. Shrink this up, move that over here. If we have to increase temperature, so we increase temperature, you're going to have to increase the volume also if you want the pressure to stay the same in the two containers. A little harder to understand, but that is Charles' Law. All right, we're going to talk about how a straw works. So, how does a straw work? Well, imagine a cup. It's got some water in here. You put your straw in. Okay. Now, there's air pressure out here pushing down on the water. We'll just call that P. Air pressure over here pushing down on the water. Same amount of pressure. Now, before you put your lips to the straw, there would be about the same amount of gas in the straw, correct? And so the pressure pushing down would be the same everywhere. So, if I represented that with arrows, it would look like this. Pressure is the same everywhere. Well, what happens when you inhale on a straw? In other words, you inhale into your mouth. You get the water to move up, but why is that? Let's move this out of the way. I'm going to make it even smaller. I'm going to redraw the picture and show what happens. So here's our container. Here's our straw. There's the water level. We'll put our straw in here. All right, what happens when you inhale? Well, what you're really doing is, let's not forget that there was air pressure out here. I'll represent that with a P, and those were because of the air particles. What you're doing when you're inhaling is you're taking the particles that were in the straw and you're basically moving them to your mouth. So you're basically decreasing the number of particles in the straw compared to the number of particles outside of the straw out here. Remember, these are pushing down on the water this way, correct? Well, you just lowered the number of particles pushing down on the water in the straw here. So the pressure inside the straw becomes very, very low, a little tiny P for small pressure, or I'll put an LP for low pressure, which means out here would have very high pressure. The air is higher outside the straw. The pressure outside the straw is higher than inside the straw. And what that does, of course, is the water will follow that path of high pressure to low pressure, and it will push the water up the straw into your mouth, and that is how a straw works. Fire extinguisher is almost exactly the same thing. The way a fire extinguisher works, something like this, I'll just try to use this actually. They put gases, it's hard to see, they put gases in here under very high pressure, so a high concentration of gas like carbon dioxide or something. But often gases are less dense than solids or liquids or other chemicals in there, so they, I'm guessing, are probably near the surface. So this would be a very high pressure in the container. Now outside the container, like where the nozzle is, there's air, but it would be atmospheric pressure, and that's low pressure compared to the gases inside. So outside of here, or sorry, in the container here, you would have a very high pressure, and outside the container, out here, would be a very low pressure. So naturally, what would happen is the gases would naturally move through here and out. But the problem is, we don't really want the gases that are creating the pressure, we want the chemical to put the fire out. So what we'll do is we'll put the chemical in here like this. Now if I just open this nozzle right here, if I just open the nozzle or push the button and open this little nozzle lever in here, the gases would go flying out, but the chemical might stay in. It's a very simple solution to this. What they do is they would put this tube actually goes all the way down into this chemical that is going to be released. And so when you open the nozzle right here, the high pressure here pushes down on the liquid and forces it out here, and then it comes out this way. So fire extinguisher works that way. Lungs, how do they work? Basically, you have a muscle called the diaphragm, and all it does is your diaphragm will actually squeeze your lungs or force the air out of the lungs. Okay. So what that does, if I force the air, now don't forget there's air outside of the lungs where your mouth is, so there's air out here. We'll call that P for pressure, so the air outside is the P for pressure. And if I squeeze the air out using a muscle, that leaves very little. So if I had a lot of particles in here originally, I squeeze them out. So I'm going to squeeze them out, and I'm going to redraw it over here with fewer particles. All of a sudden, the pressure in my lungs got very small. So now in my lungs is a very low pressure. So if I have a very low pressure in my lungs, and outside of the lungs is a much higher pressure, air is going to naturally want to go back into my lungs. So it turns out we force the air out, but the air just naturally wants to come in because of the low pressure you created in your lungs. Those are how lungs work. Well, if you weren't in class, I did this thing called water into BROAID, which is just 2 cans, and they made them of glass so you could see in them eventually, but I covered up the glass so when I did the demo you couldn't see in it. But you could see the following. You could see a glass tube that was inserted in here that came out and over like this, and that was a glass tube. And you could also see another tube that connected the 2 cans like this. Now what you couldn't see is where those tubes went into the cans. And what I did is I poured a little bit of water into here. So it's a tiny bit of water. And then out of here started coming up this blue liquid that I called BROAID, and it started coming out this tube like this, and then it just kept running. It just kept running. So I tried to get my students to figure out how this worked without me showing them. Where did the tubes go? What were the water or liquids like in the cans before we started? So I'll offer a quick explanation here. Here's how it worked. I filled this can A almost all the way up with blue liquid. Okay. And then this can, I actually did put a little bit of water or blue liquid at the bottom, and I extended the funnel all the way down here, like that. And what happened is when I poured water in here, it causes this water level to rise. And so that's exactly what started to happen. The water in here started to rise as I poured it in there. Well, what does that do to the gas particles that are in here? Well, it wants to increase the pressure because I lowered the volume, but since they have an escape route, boom, those gas particles, let me switch colors for gases. These gas particles, I'll switch it to orange, were forced through this tube into here. And what's that do to the pressure in this space right here? It increases it. You start forcing lots of gas particles in here, you're going to get an increase in pressure. Increase in pressure. Okay, so it increases the pressure. And that increase in pressure pushes down on the liquid there. Well, what I did is I had this glass tube all the way down here like that. And if I'm pushing down on this liquid, pushing down on the liquid, forcing gases in here, so the gases come through here, force down here, it's pushing down on the liquid, and it goes up this tube, out and over, and it would just keep running like that. And it basically ran until this got all the way down to here, or this got all the way up to here, and then it would stop running. I showed kids that if I pinch this tube right here, basically stopped the gas flowing through here, this gas couldn't flow through, and this would stop pouring out. That's how I made BROAID.